Kinematic positioning with GNSS. Absolute positioning, precise point positioning, differential GNSS, and real-time kinematic positioning. The objective of this video lecture is to provide an overview of the major characteristics of GNSS positioning modes applied in kinematic positioning. An understanding of that is important for the demo on RTK lib, which is the free software we're going to be using in this course. At the end of the session, you should be able to define pseudorange and carrier phase, to describe the major characteristics of absolute PPP, DGNSS, and RTK positioning, to distinguish accuracy level possible to obtain with each one of these positioning modes, to identify limitations of each one of these positioning modes, and to use DOP to evaluate results. Principles of pseudorange measurement. The basic observable of a GNSS is the pseudorange, which is derived from the measurement of the propagation time that an electromagnetic signal transmitted from the satellite takes to arrive at a receiver. This propagation time is represented by delta t in the figure and can be obtained as follows. A GNSS satellite generates a random sequence of +1s and -1s known as pseudo-random noise. It is then superimposed into the signal that is transmitted to the Earth. A receiver generates a replica of this pseudo-random noise, which is then compared with the one arriving from the satellite. Both signals are compared at the receiver in a process of cross-correlation, which yields the propagation time. The pseudorange P is then equal to the product of the propagation time delta t and the speed of light in a vacuum, represented by the letter C. This measurement of the distance between satellite and receiver contains several different terms as represented in the right-hand side of the equation. The term ρ represents the geometric distance between satellite and receiver and is essentially given by Pythagoras. The term dρ represents the error in the orbit of the satellite. The terms dt lowercase and dt uppercase represents the receiver and satellite clock offsets respectively. I represents the ionospheric delay, T represents the tropospheric delay, E sub MP represents multipath, and E sub P represents noise. Carrier phase measurements is another way of deriving the range, and here we're going to see how it is done. The signal that arrives at the receiver from the satellite, the carrier, is Doppler shifted during its trip. It is bit with another carrier that is generated in the receiver, and this carrier generated at the receiver is a replica of the original carrier generated at the satellite. The receiver then measures the phase of this bit signal. These measures are represented by the letter capital Phi in the equation. The carrier phase measurement equation has all the same terms as the pseudorange measurement equation with two differences. The first one is the ionosphere, which has a negative sign. The ionospheric delay has a negative sign. And there is a new term, N, which is the lane ambiguity, or simply known as ambiguity, which is multiplied by lambda, the wavelength, in order to express it in units of length. The ambiguity represents the number of integer cycles at the beginning of the measurement. We should also call the attention in the equation that the multipath and the noise are different from that of the pseudorange. In reality, they are smaller in value. Let's now compare the two observation equations, one for pseudorange, the other one for carrier phase. So we have here the pseudorange expression. Let me call this number 1, and number 2 is the carrier phase. Pseudorange, carrier phase, both in units of length. So let's think of meters. What is the pseudorange? Pseudorange is the product of the propagation time and the speed of light in a vacuum. So this is velocity times time equals to distance. And we said that what these pseudorange represent is the geometric distance, rho. What is geometric distance, rho? Geometric distance is the distance between receiver and satellite in terms of Pythagoras, in terms of the difference, the summation, the difference of the squares of its components. So here we have the component x of the satellite in a 3D geocentric coordinate system. This is the component x of the satellite, R receiver, S satellite, YR receiver, YS satellite, YR receiver, YS satellite. We need to understand that these terms here, we are going to start calling the attention for what is unknown in these observation equations. The 3D Cartesian coordinates of the satellite, of the receiver, sorry, are unknowns, and these terms here, the orbits of the satellite, they are given. Okay, they have to be given somehow. Any uncertainty, any error in the orbits will generate an error. So the rho represents a error in orbits, or orbital error, which means the error in the given coordinates x sub s, y sub s, and z sub s. Okay, so this term here, we are already looking at common terms. This is the geometric distance. Now we have the clock offset. This term here, lowercase dt, is the receiver clock offset. Receiver clock offset, and what happens is that the receiver, the clock on the receiver, it doesn't operates at the same rate and rate difference as the satellite clock. Sorry, yes, the satellite clock, and particularly the GPS time. So there is a synchronization. Okay, here we have the same thing for the satellite clock offset. Offset with what? With respect to GPS time, a standard atomic time. A receiver clock offset is an unknown. The satellite clock offset is given. Now we have the remaining terms in the pseudo-range equation. I is the ionospheric delay, which will have to be estimated, eliminated, or modeled. So we have these two terms here, and there is this difference in sign, which is very important when we compare the carrier phase observation equation and the pseudo-range observation equation. The term T means the tropospheric delay, tropo delay, and it will have to be either estimated or modeled. Well, we can say that we can basically say the same about the tropo delay: estimated, eliminated, or modeled. These terms here, they represent multipath, with the important understanding that the multipath error in the P, this is the pseudo-range, is larger than the error caused by the multipath in the carrier phase. And EP is just noise. Okay, and the noise level, we will see also that the noise in the pseudo-range is greater than the noise in the carrier phase. And there is one term that is missing here that I didn't say anything, which is the ambiguity. Okay, ambiguity, which exists only in the pseudo-range measurements, and again, it is an unknown. So we have to compute the ambiguity, we have to estimate the ambiguity when using pseudo-range measurements. The problem being that we're talking here about one unknown for each satellite. The good thing is that the ambiguity, they are always related to the epoch when the measurement starts. Okay, we call the beginning of the observing session. And then if a new satellite rises during the observing session, it will be assigned an ambiguity. So theoretically, it will be just the number of satellites. There are some other issues with the ambiguity. We will be discussing them in a later video lecture. What do GPS satellites transmit? It is interesting to have a look at the signal structure of GPS, because understanding it allows us to understand the signal structure of the other GNSS systems by analogy. GPS satellites transmit signals S in three frequencies in the L band. They are the L1, L2, and L5. They are modulated by several different types of information. For example, we have the carrier proper, L. We have D, that represents data, the information that is injected to the satellites, and it is superimposed on the carrier. This is done, computed from the master control station. P and C represent time marks modulated on the carrier, as step functions. These are the pseudo-random noise. What we have then is that all satellites transmit this signal L1, which contains carrier L1, the stream of data, and the pseudorange P and pseudorange C or CA. Older satellites would not transmit the C pseudorange, only the P. Now, new satellites, they all started transmitting a new C code or CA code, which is L2. So, which means that signal L2 is very similar to that of signal L1. The carrier, data, P code, and C code. And there is even a newer generation that transmits a third signal, L5. So that's important because we may have receivers, GPS receivers, capable of tracking only the signal L1. They are single frequency receivers. There are others that track both signal L1 and L2. There are dual frequency receivers. And there are receivers that track signal L1, signal L2, and signal L5, and they are obviously triple frequency receivers. Again, I'm talking here about GPS. There are other GNSS systems, and there are receivers capable of tracking all signals from all systems. They're called multi-GNSS receivers. It is very important to understand the limit that pseudorange and carrier phase have as far as the measurement goes. This limit is ultimately defined by the noise. Sources of noise include the electronics, cables, and even variation temperature can be a source of noise. There is this 1% of wavelength rule that allow us to have a good understanding about noise level. Let us consider first the carrier wavelength, which is equal to 20 centimeters. Applying the 1% lambda rule, we would have then a carrier noise equal to 0.2 millimeters, but we may have noise that goes as much as up to 5 millimeters. Looking now at the pseudorange, considering the wavelength of the CA code equals to 300 meters, the 1% lambda rule would indicate us a noise equal to 3 meters, but it can be as low as 1 meter. Now, there are special receivers, for example, narrow correlators, that can measure CA code pseudorange with a noise of 10 centimeters. The P code pseudorange would have a noise of between 10 and 20 centimeters. There were receivers which could not decode pseudorange measurements. These receivers would square the L2 signal, therefore squaring its noise. Codeless receivers are rarely used now. Absolute positioning. Absolute positioning is also referred to as point positioning. Its primary objective is to serve as navigation, plain and simple navigation, and to offer first approximation solutions. It uses pseudorange, broadcast orbits, and broadcast clocks, and it is a typically single frequency solution. And it uses undifferenced observations. In other words, the pseudorange measurements as they come. In GPS, there is a distinction between what is known as the Standard Positioning Service, SPS, and the Precise Positioning Service, PPS. The Standard Positioning Service would be a service that was built for civilian use, and the idea is that it would be based on CA code, whereas the Precise Positioning Service would be of more restricted use for military use of the U.S. Armed Forces and also for NATO allies. The accuracy of the civilian use, the SPS, is, and here I'm quoting some numbers to be on the conservative side. Horizontal around 3 meters at 95% confidence level, and vertical precision at 9 meters at 95% confidence level. It gets better if a was correction is used. So the limitation of absolute positioning using pseudorange and broadcast orbits and clocks is the accuracy. Dilution of precision is a factor that indicates if the geometry of the satellites on the sky is affecting negatively the measurement accuracy. Let us consider sigma as the positioning accuracy, sigma sub-zero the measurement accuracy, and DOP the dilution of precision. So the very first equation, we can see that the DOP is increasing the measurement accuracy. If DOP equals to 1, the positioning accuracy will be equal to the measurement accuracy. But if DOP grows in value, it indicates that the geometry is getting worse. For example, instead of being evenly distributed on the sky, the satellites will be grouped in a particular portion of the sky. Therefore, a larger DOP will be multiplied by the measurement accuracy, so the numerical value of the position accuracy will be larger, therefore indicating a lower accuracy. So that's the paradox of the big number indicating something that is worse than a smaller number. A larger value of accuracy is worse than a smaller value of accuracy. So higher accuracy indicates a smaller value. There are different DOPs. There is the vertical DOP, which is the DOP for the height. There is the horizontal DOP, which is the two-dimensional DOP just for horizontal position. The DOP related to time, which relates to the parameter dt, the receiver clock error. There is the PDOP, which is the DOP for the 3D positioning, and the GDOP, which includes all components, latitude, longitude, height, and clock offset. The smaller the DOP, the better the geometry, the better the solution. And typically, we think of a DOP that is less than 4 as indicating good geometry. Here we have a geometric interpretation of GDOP. We have 4 satellites, and you know that we need 4 satellites to solve for the latitude, longitude, height, and clock offset. And here we have the receiver. So the GDOP is the inverse of this polyhedron formed by these 4 satellites and the receiver. Precise point positioning. Precise point positioning is absolute positioning using carrier phase measurements and better quality satellite orbits and clocks than the ones broadcast in the navigation message. It is intended primarily for high accuracy positioning and establishment of base stations. It uses carrier phase and also pseudorange. Typically, the orbits and clocks come from the IGS, the International GNSS Service products, and also it is based on dual frequency measurements, but in the same way it uses undifferenced observations. its accuracy is much lower than the absolute positioning. For a static positioning, it reaches centimeter level or better at 95% confidence level, and in kinematic positioning it is at the decimeter level, and now it's a little bit more difficult, and it can get worse than that with a confidence level of 95%. The limitation of precise point positioning is the convergence of the solution. It takes several minutes, can be a few minutes up to 20 minutes depending on the situation, for the solution to converge to the sought for accuracy. Differential GNSS. Differential GNSS is a technique that allows position of a rover receiver B, as a function of a base station A of known coordinates. Receiver A and receiver B, the rover, they observe the same satellite I at the same time. We have here the pseudo-range that is measured from the receiver A, and we have the pseudo-range measured from receiver B. Because we know the coordinates of A and we also know the coordinates of the satellite, we can compute the geometric distance. If we compare the geometric distance with the pseudo-range, or the pseudo-range with geometric distance, we are going to have these differences. So at every epoch, observation epoch, we are going to have a difference, and let me call this difference delta P. This difference can be made into a correction that we call the pseudo-range correction. And at every observation epoch, the pseudo-range correction could be transmitted from an antenna, for example, all the way from an antenna close to the receiver, known receiver, to the unknown receiver, and this unknown receiver would then apply the pseudo-range correction into its pseudo-range observation. Now, if the interval, observation interval, is very high, we can do the following. We can compute a pseudo-range correction, not for every observation, but say for observation every 15 seconds. 0 seconds, 15 seconds, PRC 30 seconds. And then we can compute the rate of change of the pseudo-range correction. Okay, so we can rate of change from 0 to 15, the rate of change from 15 to 30, and every time now we make a correction. The corrections will take place at every 15 seconds. They would have the pseudo-range correction and the rate of change, which means that the receiver or the computer associated to the rover can then apply the pseudo-range correction computed directly from the rate of change to the pseudo-range that it observes. Basic idea of DGNSS. A GNSS receiver at a known location that we can call a base, monitor, or reference station observes all visible GNSS satellites. The geometric range or geometric distance can be computed from the known reference station's coordinates and the given GPS satellite ephemerides. it is then subtracted from the measured pseudorange. The difference between the measured pseudorange and the geometric distance is what we call the pseudorange correction, PRC. So what this PRC contains? It contains the satellite clock error, the satellite ephemeris error. It contains the receiver clock error of receiver A. It contains ionospheric delay, tropospheric delay, and the receiver noise from the receiver A. What happens in here is that we are making an assumption. The assumption is that the observations, the pseudoranges observed by A, by receiver A, and observed by receiver B, they will have common errors. Their errors are common. So, of course, they're observing the same satellite. The errors from the satellite are the same, satellite clock and satellite orbits, the ephemeris. But when we talk about ionospheric delay and tropospheric delay, what happens is, if the receiver A and B, if the receiver A and the receiver B, they are close together, certainly they're crossing the sky about the same place. So what happens is that the ionosphere and the troposphere, the delays, will be similar. But if the base station is far away from the rover, now the ionospheric and tropospheric delay will be different, because they're going to these observations are crossing the atmosphere at different places. So even though we can say that certainly the satellite errors would be common, the ionospheric delay and the tropospheric delay, we can think of them common if the base station and the rover are close by. Now there is things that are really not the same. For example, the receiver clock errors. Well, this is just for receiver A. The noise is just for receiver A. So it's not for receiver B. So the assumption of common errors is actually which is a characteristic of DGNSS, is also a limitation. So the pseudorange correction changes much slowly over time than the pseudorange, which is something positive. So when the receiver, the base station, transmits pseudorange correction and the rate of change, these are smaller numbers. The GPS reference station determines also the rate of change of pseudorange correction, as we talked. And they're updated at certain intervals and transmitted to the rover. What happens then is at the rover, these values are applied. So the pseudorange, consider a generic epoch t. The pseudorange correction at epoch t is going to be the pseudorange correction at the epoch it was computed, t sub 0, plus the rate of change of the pseudorange correction between the time of the observation t and the time when it was computed. So these PRC sub IT will then be added to the pseudorange at that particular epoch, and the mathematical equation can be simplified just dealing with the unknown parameters at the receiver, B, which are the coordinates of the receiver, and the receiver clock offset. These corrections are transmitted following the RTCM SC104 data format, and the accuracy that we have, typical accuracy of DGNSS, is 1 meter for horizontal position and at 95% confidence level, and the vertical at 2 meters, 95% confidence level. And of course, we have the limitation that the errors will grow with distance from the base station. Satellite-based augmentation systems, or SBAS, is an idea that flourished to try to account for the limitation of DGNSS, namely the correlation of errors with distance. SBAS is also referred to as wide area DGNSS. So the objective is to reduce the errors due to distance from the base station, and a network of base stations are used to compute corrections, including corrections to orbital errors, satellite clock, and ionospheric delay. So instead of a single DGNSS station, what we have is a network of stations. These network of stations, the observations will be, they are transferred to a computing center, which will compute these corrections that now are different type of corrections. There are corrections to the orbits, corrections to the satellite clocks, and also the ionospheric delay. So we can also have a model computing tropospheric delay. Therefore, the ionospheric delay, the tropospheric delay, which may be growing with time, they will be now accommodating these growing with distance, I'm sorry, of baseline length. They will be now representing the region where these base stations are located. So these corrections are then transmitted to the user's equipment by geostationary satellites. And there are a few examples of existing WADGNSS, this SBAS, around the world. We have the WAS system, which is the SBAS in the US, is known as the Wide Area Augmentation System, which covers the continental US plus Canada and Mexico. We have EGNOS, which is the European Geostationary Navigation Overlay Service, which obviously serves Europe. Japan has its own, it's called Multifunction Satellite Augmentation System. India also has a system that's called GAGAN, GPS-aided Geo-Augmented Navigation System, and Russia is developing its own, known by the acronym SDCM, which stands for System for Differential Correction and Monitoring. We have already seen that there is one way of positioning using carrier phase. That's precise point positioning, in which we use only one receiver. Now we are going to talk about the use of 2 or more receivers with carrier phase kinematic. So what we have is carrier phase measurements, which allow us to reach centimeter level accuracy, and relative positioning. So relative positioning, of course, we have a base station A, we have a rover B, okay, so they both will be observing the same satellite. So we have a base station here that is formed. Of course, the idea is that the rover B is moving around in kinematic mode. What happens is that we can have a real-time solution, or we have a post-process solution. So in real time, of course, the observations from A will be transmitted to B, which will apply them. In post-processing, the observations will be stored, and then they will be, of course, post-processed. The idea is that RTK will provide a very good quality centimeter level accuracy, but it's going to be using, for example, broadcast orbits and clocks, whereas in post-processing mode, we can wait a few days and use IGS products. So we can do better quality control. So post-processing usually leads to a slightly better accuracy solution. And but there is this sentence here to add to make a comment about that. There are some softwares that would allow what is known as the playback solution, and the playback solution for the RTK, which means that it's like a post-process RTK, but it is done without the quality control. So the idea here is to mimic what an real RTK would be. We're using the same figure that we used before for DGNSS for RTK. We have the same base stations A and B, the same satellite I, but here what we are observing is the carrier phase A, carrier phase B, and the transmission of observations will be either by radio or by internet, will be the carrier phase. Carrier phases will be sent from the rover to the base station. If you recall, we mentioned before elsewhere that kinematic positioning has a problem in terms of redundancy. In static positioning, we may have redundancy by repeating the measurements or by adding more external measurements. In a GNSS context, that would be adding an additional base station. In kinematic positioning, we cannot repeat the measurements because the unknown point is moving. So every time the receiver that is moving is collecting observations, it's collecting new observations. It's in a particular spot, then goes to another spot, new observations, go to another spot, new observations. The new observations are the observations at that particular time and space. And this creates a problem, of course, in the sense that we have more parameters to solve for. Let's look here at the static case and look at the geometric range, because things will be more clear in here. What we have are the observations of the satellite and the receiver. X, Y, Z are the receiver. Well, not the observation, I'm sorry. These are the coordinates of the satellite, okay? Component S, component X, Y, and Z of the satellite. And of course, the satellite is moving, therefore these coordinates the orbits will be changing all the time. But the receiver, the unknown receiver, is static. Okay, so which means that we have only 3 receiver components as unknowns, and of course we have the receiver clock. In a kinematic case, it is the opposite. I mean, it's different, not the opposite, it's different. Because we have, again, the orbits, which are given, by the way, you know that, the satellite orbits, and now the receiver is located at a different position at every single time t. So at every epoch, we have 3 unknowns. Now the clock, we can estimate the clock at every epoch, or we can estimate the clock as a function, which is usually the case. But the fact of life is that we have, at every epoch, we have the 3 coordinates, the three unknowns as the 3 components of the station, of the place where the rover is. So there is a time dependence for the rover. If we're dealing with carrier phase, things get a little bit messier, because here we have a single difference. We have how many unknowns? 3 per epoch. These are the x, y, z coordinates of the components of the coordinate of the receiver. Then we have the ambiguities, number of ambiguities. Number of ambiguities, we have 1 per satellite. Okay, 1 ambiguity per satellite. So the ambiguities, okay, is actually equal to the number of satellites. And we have the receiver clock. If we want to estimate the receiver clock at every epoch, we're going to have 1 unknown for every epoch. If you do a double difference, what we have, again, is still we have the x, y, z components as unknowns. The receiver clock is eliminated, and we have number of ambiguities minus 1. If we do a triple difference, we have only the x, y, z coordinates. The ambiguities are eliminated. So, which means we have to think about the ambiguities in here. If we can solve for the ambiguities as real numbers, we get a better solution. Okay, so in real time, in real time, things are messier. Okay, we have to estimate ambiguities on the fly as we move, or we have to get rid of the ambiguities. So not first, we have to get rid of ambiguities. So if you want to estimate the coordinates x, y, z without ambiguities, we can just use a triple difference. If you want to estimate the ambiguities, we can use double difference, which is usually the case when we deal with ambiguities, and we are going to estimate it on the fly. And we are going to estimate on the fly, and here's the thing, we can estimate it as a real number, real number or as an integer number. To solve for integer number, we have to look into special techniques. So anyway, the discussion on ambiguities is part of a dedicated section that deals with ambiguity resolution. Limitations of real-time kinematic. Range. If we're dealing with a radio link, the range is typically up to 10 kilometers. The errors of atmosphere, they grow with distance between the base station and the rover. Because we are dealing with carrier phase, we will be dealing with ambiguity. So we can either fix it, solve as an integer number, or solve it as a real number. It is more difficult to deal with the ionospheric delay if we deal just with a single frequency, dual frequency receivers. We can formulate the ionospheric delay free combination. And we have the issue of range, again dealing with radio link, because if you use, as usually the case, ultra high frequency or very high frequency, it requires line of sight. Latency is has to do with the age of the information. So a good definition of latency is time spent for the message or the observation to travel from the base to the rover via the link, plus time for the rover takes to compute its fix, its position. Sampling rate and reliability. This table makes a comparison between real-time kinematic and differential GNSS. So it is useful to look what they have in common and what they have, what they don't have in common, what makes them different. So in black, we have the difference. RTK is on this side, DGPS on this side. RTK offers centimeter level accuracy, whereas DGPS or DGNSS offers meter level accuracy. RTK is based on carrier phase measurements. DGNSS is based on pseudorange measurements. RTK requires simultaneous satellite observations. DGPS, depending on how it is built, will require simultaneous satellite observations or not. Raw carrier phase, and we can think here, for example, if the observation rate of base station and rover are different. Okay, we can still apply the corrections because DGNSS corrections, because we have the rate of change of the pseudorange correction. What is transmitted In RTK are the raw carrier phase observations. In DGNSS are corrections to pseudorange. Now we have in blue what we can consider as common. Both provide solution real-time. Both requires data link, and data link here can be radio, can be internet. There are limitations. Limitations in terms of range, limitation in terms of latency, in other words, how long it takes for either the DGNSS corrections or the raw carrier phase to arrive at the rover. Issues with sampling rate. We can think, for example, that things get more demanding if the sampling rate is very high. One thing is to transmit information every 10 seconds, the other transmit information every second, or if you think even in terms of higher sampling rate, things start to become more demanding. And there is also issue of reliability. And the reliability here has to do with, well, we can, for example, redundancy. We cannot have redundant solutions. The solution is what we get. So it becomes more difficult doing quality control. It is possible, but it's more difficult. There is a concept that is known as network RTK, which has been designed to bypass this limitation in range that RTK may have if using radio link. So the idea here is that we have now a geographical area, okay, that is covered by this network of receivers, and these receivers, they all send their observations to a central computer that will be generating virtual coordinates, well, we may have this point here. This point here is the location of a virtual station that is in the center of the surveying area. So within less than 10 kilometers, for example. Nonetheless, what this virtual station will be the information that we're going to have generated from this central computing facility to the virtual station will be observations. So there will be observations as if there is an actual base station here. Okay. And what network RTK can also provide would be corrections for the atmosphere, ionosphere, and atmospheric delay, tropospheric delay. One thing that we certainly will not have with this virtual base station is the receiver clock offset. So the only receiver clock offset that we need to estimate will be the one for the receiver of the rover, depending on the type of solution. If it's double difference, of course, it's going to disappear. So that's a a system that you may find here and there for surveying. Not much in kinematic positioning per se. These would be more surveying, but that's interesting to mention. There is also an attempt to use PPP with extra information. The big problem with precise point positioning is the convergence time. Now, real-time kinematic, there is not really a problem with convergence time. So there is actually some software, commercial software, and commercial solutions that offer what is known as the PPP-RTK, which is nothing else an attempt to decrease the convergence time of PPP by including atmospheric corrections based on observation data from local RTK or from network RTK. So the idea here is to have fast convergence and then rely the rest on just the PPP solution. Take-home message: absolute positioning provides between 3 to 9 meter level accuracy. Precise point positioning provides typically sub-meter level accuracy, but convergence is an issue. Differential GNSS provides typically between 1 to 5 accuracy globally today, but uncertainty grows with distance from base station. And RTK provides sub-decimeter level in real-time kinematic, but range is limited due to radio link. And here we have references that you have access to. Wells et al. Guide to GPS Positioning is available on this link. We'll have also available Hoffman-Wellenhoff book called, and others, the book called GNSS. And here are the reference, the chapters and sections where you find material about what we discussed.